So once you have this organized in front of you, one way to do this and make your life a little easier, and I'm zooming in here, but then it gets a little bit harder to follow now. So one strategy is you don't want to change the alignment of your sex stratification and the actual exam score. So one way to do that, so there are more elegant ways, but the simple way at this point is essentially to copy the first two columns and insert them before each exam. So if you just copy them with Control-C, Command-C, and you insert them before exam 2, and here it asks you insert copied cells, and you say yes, and you basically do the same thing with exam 3. Oops. So you need to copy it then again and do the same strategy for exam 3. This will now allow you to do two things at the same time. So firstly, it will allow you to sort. Yeah, please grab a chair. No, please sit down. Oh my God. No, please just. Chair, please. Okay. All right. What you essentially do, you try to keep that alignment. So you copy. So it's was okay. So let's go back. You select the first two columns. You select. We need a bigger screen. You should write a petition to the dean's office that we need bigger screens here. You can also go on Zoom. Those of you that sit in the back, you can also go on Zoom, so you see it larger on your screen. All right. So what you can do, you basically select column A and B. You copy that and you go and select now the column with exam 2, and you select insert copied cells. Insert copied cells will just basically copy these two columns. It inserts your gender stratification in front of your exam scores. If you then press Command-C again, you just select same fashion, you do the same thing, you go insert copied cells, and now you have that alignment replicated. Oh, wow. I'm so sorry. Okay, is everybody? So it should be semester side on exam 1, semester second, exam 2, semester second. Exactly. With the idea, and this is why R is a powerful tool, because in R you don't need to copy and to do this redundancy in Excel. It's just a little harder to do that, right? So the next way you can approach this is then basically, since you only need that stratified as per gender and scores to build your tables, you select exam 1. So this is here semester, sex, and exam 1. You go on data. How do you just click A, B, and C? I just select these 3 columns, and now I can sort these 3 columns independently from the others. So I can go on sort by data and sort the first 3 columns. I selected the first 3 columns, and I'm sorting only those 3 columns. And you sort them in 2 approaches. You have 2 levels of sorting. First level is sex, right? Because you want to stratify it as per gender. Then you stratify it as per sex. And if you click on the left side on that plus, you can create a second level of sorting. Where's that? Oh, what's on the bottom left? This plus. You click the whole chart. Not just 3. Just exam 1 for now. And then by exam 1.
all I have is two column A, column B, or column C. I don't understand. You have to copy A and B.
So the header is written in the first line. So you select then in a second level sorting, you sort it as per score.
So you do sex and then exam one?
You do first, no, yeah, just select these three.
Yeah, I did.
First sex.
Oh, I have to click it first? And then
No, you have it already. First sex, and then exam one, smallest to largest.
that's good, and then I click it?
That's
I
it.
have to do that for each exam?
You do that for each exam.
I had to make two tables, I didn't know I could do that.
No, but this comes to the same end, right?
Yeah, but then it was like, it's so much easier like this. I don't have the plus. You know the plus that you want to make another column?
Take this plus. Like this plus. It's the same concept, right? You just add different levels of sorting.
And I'm doing this by exam one.
First sex and then exam one, yeah.
So the second one is exam.
Correct. Smallest to largest.
These would be cell values.
That's fine.
Yeah. And then A to Z and smallest to largest.
Smallest to largest, yeah. Or largest to smallest, whatever you prefer. Whatever is easiest for you, right?
How are you doing it on the board?
Hmm?
How are you doing it on the board?
On the board.
Yeah, like when you show us right now, you're gonna pick smallest to largest. I just want to copy.
So this is smallest to largest, yeah.
Okay, thank you.
So, but again, I'm winging it, right? So you gotta just use your own intuition. What is easier for you to count? It doesn't make a difference because essentially what you want. So now you have sorted this. Now you do the same exercise for exam 2.
Wait, I just was okay.
You do the very same exercise for exam 2. Again, sort by sex
Wait.
plus sort by exam 2. Smallest to largest, and then I do the same exercise for exam 3, sort by sex, plus sort by exam 3, and okay. So now you have the perfect starting ground to count whatever you need to count, right? So, but you see, this is the reason why I make you do this exercise, because that's just, it's a learning curve, right? It's something that you need to have practiced once, and then next time you're gonna laugh about it and you know how to approach it, right? That's the idea. It's not super difficult, and I'm well aware of that. So now, and the next thing you need to do, and that's simple, you have three different tables that you built. So you have then the grouping, I don't know what I did, 51 to 60, 61 to 70, XXX. And then you have here the count. Then you just keep on counting, and you count, or you can do the count if function. Those of you.
What do you mean by regular count? You mean regular count and then?
Yes, you can also do a count ifs. You remember? Yeah.
Equal sign?
No, you can count it through manually. You get comfortable with the exercise. Get comfortable.
How many there are in from 51 to 60? We count how many exams there are between like 51 and 60.
Correct.
Okay.
Correct.
For each exam, it's a different one. Okay.
Yeah.
Yeah.
So the idea of statistics is to aggregate data, right? This is not I would never analyze data that way. And you will see it for the midterms, because I will present you how I'm looking at data. So I do class distribution. So this is my guiding star, how difficult the exams are, where the class stands. So I do my own stats on you guys. I do.
Yeah, makes sense.
Because you want the ceiling effect. On the end of the course, I want the ceiling effect, right? I want everybody to do well. Yeah. So
Thank you.
you gotta do your own stats.
The hardest part, I think, also is just setting it up. Because sometimes it gets confusing. Like when I set it up, it's like, well, you know how you want to do it first before you.
You need to think it through first. What is the outcome? So shape follows function. You need to understand, what do you want? What do you want the table to tell you? And this is part of that learning curve. You need to organize yourself in how am I thinking about this? Yes.
Yeah, can you show us again how to count it?
Why 60 here now?
You want it? Yeah. Well, essentially, yes, it's easier. Yeah.
Well, I've just been doing equals count and then like parentheses and just like selecting stuff.
Yeah, that's one way. Okay, so now you challenge me because count ifs is a little bit of a harder formula. Yeah, yes, yeah, of course. There's a formula for everything.
Yeah. I did all of it.
Good, good, good. No, don't worry. And your most powerful friend when it comes to stats, programming functions is Excel. This is true for, no, it's Google, because all these things I explained on Google. For R, you have the most powerful tool. You have a very small fraction of analysts who actually understand every function they want to do. Everybody goes to forums and fora where basically problems are being discussed. And you see, so one person is an expert in one function, one package. Another one is an expert in another function. There's a very vivid knowledge exchange. It's a community, the analytic community is a very strong and a very altruistic community. If you have a problem, you will find a solution by that within the community. This is why the forums for R, Python, all programming languages, they're very strong. There's a very, how should I say, a very strong sharing mindset. It's fabulous. It's really fabulous. You will post a problem that is very specific. The experts, the forum moderators, they will guide you to previous posts that discussed exactly that question, but you will get to your solution within days.
Do they do it for fun? They're part of the forums for fun? Or it's like their job, people have jobs to get into these forums?
Well, there are some commercial ones, but mainly everything is open source. R has a long history that basically came out of the Technical University of Vienna and other universities worldwide that collaborated and built a consortium that took C++ and formed this consortium and started programming that software. And this is a living and breathing animal that grows and evolves and changes. So it's for free. Everything is for free. Yes.
So for the D, E, and F, so this one is ordered A to Z, but this one is smaller to larger.
That's fine.
So, but then the other one is Z to A.
Well, that's for you to judge which one you want.
Okay, but then.
But you just don't mix it up. Make it in the same fashion as here, because then you have the man all in one column, and they are aligning, right?
Because the other one was like smallest to largest and then largest to smallest. I don't know why this is like the A to Z option.
Because it's a categorical variable, it's a nominal variable, where basically M is before, or F is before.
So it's supposed to be, but it's not going to be the same as this because that one, this isn't A to Z.
No, the sex stratification is going to be the same. Has to be.
Oh, it is.
Just within the gender, it's different because different people have different scores with each iteration of the exam. Yeah.
Okay, I lost you since the beginning, so I'm gonna rewatch it. But how do I make it into this date and not January? Because it's right in January.
Don't worry about that. Don't. You can make a right click on it. And you go on format cells, but this is just an aesthetic. Don't worry about it. It's really more about the counting. So count ifs. No, it doesn't.
What should I do after this so I can try to follow?
You sort it by biological sex.
Each column.
Correct.
Okay. Thank you.
This is D. Let's see. 30.
What's going on? How did you get that formula from?
Okay, criteria 1 is, okay, quotation marks greater than 50. Criteria range C2 to C30. And this is more than 61. Okay, so this is the function. This is the function. So you have a count ifs function in which you define several criteria.
So how do you get to building?
Yeah, you just enter count ifs and the open parentheses, and then you can click here on fx, and that opens the formula builder. And here you first enter the range, which is for exam 1, it's C2 to C30, all the way to the end. As criterion, you enter it's greater than 50, which is starting with 51. Criteria range 2 is again C2 to C30. And the criterion 2 is it's smaller than 61, which ends with 60, right? Because it's integers and smaller equal. So if I would do smaller equal 60, would be the same than smaller than 61.
How do you get that? How do you get that pop up again?
Open right equal sign, count ifs, open the parentheses, and click on fx, the formula builder.
Oh, this count is has to be in all capital.
Doesn't matter.
Wait, then what do I do in the formula builder?
This.
Insert function.
So this is your range.
For every function.
This is your range of data. This is the criterion. It's greater than 50. This is the criteria range 2, same range. Criterion is smaller than 61.
Interesting.
Yeah.
Can you drag that down? Can you drag that down or no?
Yes, you can.
But not for others.
Yeah, but I'm not gonna do this now.
Wait, can I see?
Okay, we can do it for each one.
Yeah, but now you do less work, right?
I didn't get that.
Thank you. Look,
I didn't get that.
All right, so you have the recording. The only thing you need to do is replicate this formula and apply it for each of your ranges. Saves your time, right? Okay,
What was the next one?
good. So you have it on the recording, you can replicate this. Okay. Okay, I can't.
Oh, wait, you're doing it in order? So my school has been
So the way how you could drag it down would be in this fashion, would be 51 and 60, where you're stating 61 and 70. So count ifs, here you need to change then the criterion as smaller than, greater than this.
What about the count, Eric? The count line?
I don't know. L4.
What are you doing now? Oh, you just moved over the count row?
No, it doesn't do it.
Some errors popping up.
Wait,
Literally, I did it by hand.
L4.
Professor?
Yeah. Okay, I would need to play around with it. Forget it for now.
I actually think it's 5 because it said it's 60.
Okay, so forget this for now.
If we didn't use the function, you still get
Hmm?
Is it okay?
If you figure that function out, yes, you get extra. No, not extra credit, but you get full credit. Full credit on the smiley face.
Yeah, I can't wait to see smiley face. You did it by hand. Yeah, I'll do it by hand. If we count by hand, we get extra credit.
Nope.
Smiley face. Smiley, so we're not getting points off for not doing the formula for counting. Okay.
I have a question.
Yes.
So y'all put it in the count if function and got 6 for exam 1, but if you count it out, because like 60.5, I guess they may take differently, but what? Samantha.
So this is overall, right? So you have here 1, 2, 3, 4, and it counts to 60.5 as.
I didn't catch.
That's fine.
Yeah, I got.
I'm using 60.5 as like I'm using all the 0.5 as up.
Well, it's smaller than 61. You could do, you could rechange it to smaller
I
equal.
already did so much. So
I read it.
Smaller equals 60.
I counted it up.
Yeah.
We could do less than.
That's fine.
16.9.
That's fine.
Okay. Yeah.
Yeah, so smaller than 60.4 or smaller than 60.5 would be the formula.
Does this look right?
Yeah, I would do it in one table. Exam 1, exam 2, exam 3.
But otherwise,
It's easy.
it's good though.
Yeah, the format is fine, yeah, but I wouldn't do it like that. I would really do it in one table.
How do you?
So you essentially you compare them, and this is the table. Proportion, percentage. We know how to calculate it. We do an average. We do a standard deviation, and then we do the same exercise for males, and then for females. We don't need it now. All right, sounds good. Okay, so you have to some recording, reproduce it according to the instructions and recording. Now we need to get started with lecture. Now we're running out of time. I'm sorry. Okay. All right. Okay, so this was a little bit of an excursion in the homework. I hope the instructions are now clearer. Things are clearer. Please utilize the discussion board. I will be, can we please focus? Thank you. Utilize the discussion board. Give me a poke via email that there is a question on the discussion board if I don't respond within 24 hours. Okay, we're talking today about sampling and probability, which is a very important topic to keep in mind because this will be where we are hitting running ground after the holiday break. So we have talked about two different samples. So everything evolves around samples, as you can imagine. We're having populations and we're having samples. You are studying, studies are only conducted in samples for practical reasons, right? Because you can't study an entire population. You can't study an antihypertensive medication in an entire population just for the purpose to find out whether medication works or not. It's just not feasible. So for that very reason, you sample smaller subsets of your population, which you hope is representative for your population. So when you sample, you basically, you want, and this is the perfect world scenario, you want a random sample. A random sample means that you have an overall population and you take from all ends of this normal distribution curve from the population, you're taking equal from each level of blood pressure, cholesterol, whatever you want to sample. So that overall the distribution of your sample is identical to the distribution of the population. This means that the blood pressure in your sample is the same as in the population, and when you employ your antihypertensive medication in that randomized controlled trial that you want to conduct, basically shows the same dynamic that the population will show as well. Problem is, it's a perfect world scenario that doesn't exist in real world, in real life. Fact is that pretty much all the studies that are being conducted on medication, on whatsoever, are usually from non-representative samples. They are to some extent representative, but most studies are done in a population that is younger, more likely to be more educated. There are always reasons why they're participating in studies rather than the overall cohort. Also, you have sometimes interventions that you can just not do in a population. So when you study blood pressure medication, you're not going to do it in the sickest of the sickest and the oldest of the oldest, because it comes with a risk, right? So you basically, you try to create somewhat representative samples of your population and you study those. In most cases, you're studying something that is called a convenience sample. A convenient sample is a sample that's sampled because it was convenient to study that particular sample. So to put this in perspective, when you would, for example, try to make a survey about the perception of, I don't know, what's a good example? So my examples are traditionally always terrible, but basically you're studying an opinion on a political topic, and you stand right in front of Bloomingdale's, and then you do another sample where you stand in a different area of New York, or you use different areas. You will get different opinions towards topics, perceptions. You will get different cholesterol levels, for example, in right next to terrible examples. Okay, so you basically the convenience sometimes is your enemy when it comes to finding representative samples, and that's the take-home message of convenient samples when you study readily available samples. College students is the example that Nolan and Heinz are stating here is also true, because you're looking at, usually in many colleges, you look at a higher socioeconomic level, you look at a more sophisticated crowd, you look at higher levels of comprehension. So it's again not comprehensible. You have a question?
Yeah.
Yes.
About what you said about the first thing you said, what does it mean that you're taking, when you have a random sample, that you're taking it from all ends of the
Yes, so you basically have so a population has larger extremes as a sample in most cases. That means that you will not sample many extremes if you randomly, if you take a convenient sample. That means that basically your sample distribution would identically represent your population. So it would look this. So you remember the normal distribution curve? So you have a smaller normal distribution curve
for the sample.
For the sample. That would be a random sample.
So if you did a random sample and you did it really well, and you have all diverse parts of your population, as a normal distribution to look the same for the sample population.
It should, yes, it should, but it doesn't, and that's the point, because usually it's a convenient sample. And so we will, with hypothesis testing, with the SET test, we will look at methods how to compare your sample to a population, and to compare this in terms of their distribution. And so the convenient sample here really is to be kept in mind. It's basically a readily available population, readily available sample population that essentially does not necessarily represent the population, and that's the issue. So a random sample, and now we're coming to your question. So every member of the population has an equal chance to being drawn. So the distribution curve, if you think of the frequency polygon, where you basically have a representation of different fraction of that population. So less likely in the extremes, less likely to be presenting with high cholesterol, and in the lower tail was a smaller probability to have an individual that has a smaller cholesterol, or lower cholesterol, but the bulk will center around the mean and the median, as you remember from the central tendency class. So random samples are almost never used in the social sciences because they're just not readily available. You can't sample from the entire spectrum of socioeconomic levels or levels of education, levels of political opinions, whatever. It's just impossible to really get this random sample. And I keep on talking about political opinions because this is where most of you probably have seen examples from statistics. We will talk about the confidence interval, where basically exactly this is brought into practice, where you have a so-called margin of error, where you basically you estimate what the population's opinion is in true reality. And we will calculate this margin of error in class 9. No, chapter 9. So random samples are almost never used. It's mostly a convenient sample because you need to find somebody who actually is willing to sit down with you and go through a 30-item questionnaire. That also requires time, which also renders a convenient sample more easier to study. It's difficult to access the whole population, and therefore you need to determine how you select your samples. So convenient samples, those are samples that use participants who are readily available. Why would you use the convenient sample? Because it's more convenient, it's easier, it's more efficient, because doing studies takes a lot of time, takes a lot of money, takes a lot of resources. So therefore, convenient samples are just easier to study. A convenient sample might not represent the larger population. As said, it may not capture particularly the extremes. It usually doesn't capture the extremes. So you will always have a deviation from population means and the distribution of the population. What's important in this context is generalizability. And generalizability is the technical term for exactly this representativeness. And so there are ways how you can formally study that. The one sample set test is one that you essentially can conduct or can employ to essentially test for this quote unquote external validity. So this is a synonymous use of generalizability, and external validity means the same thing, means that your sample is representative for the population. Can be improved with replication means that if you see a certain dynamic in your sample, and you see it again in a different sample that differs also from the population, but basically differs in a different direction, and then it's also being replicated by another group in Singapore, and then a group in Germany, and a group in Australia, and several authors have seen the same dynamic and have seen the same finding, you know that your findings are generalizable to the population. Yes.
It is basically saying that convenient sampling is inherently flawed, but these are ways for us to try and combat that to make it as valid as possible.
Exactly. You ascertain your findings and you ascertain your insights. And you make sure that replication is actually the most important thing in research. So you have a hierarchy of scientific evidence, how much scientific evidence essentially is worth. It's almost literally worth. So you have scientific grades. And the highest grade of evidence is brought to you by randomized controlled trials, because you have minimized confounding with the randomization of the random assignment. The problem is the selection bias or the lack of generalizability in a convenient sample comes to effect because the dynamic may not be generalizable. So then you need to replicate it. And we will talk about meta-analysis at one point, which I forgot which chapter. And meta-analysis are basically a tool to depict the results of several randomized controlled trials or several trials and allow for you to see how strong is this effect, even with different samples, different sample populations. So a volunteer sample, this is the worst case of it. So because this is a self-selected sample, and this is exactly where you introduce confounding. And this is unfortunately quite commonly seen nowadays with something that is called crowdsourcing. Crowdsourcing is essentially you have a questionnaire that you're interested in, and you basically you blast up an email to 100,000, 150,000 people, and then you wait who answers your questionnaire and what responses do you get back. The problem is these people that will select to answer this questionnaire, there may be a reason why they're doing it. Either they have too much time, or they I don't know, they don't like the product, which is also, we're going to speak about this testimonial bias later. So there's a reason for that. And the same problem you have with the Mechanical Turk. I don't know who of you knows that. That's an Amazon service that essentially allows to earn money by answering surveys or giving opinions or doing little tasks that are being solicited there. So this is network sampling, online sampling.
So what is that then? The stat comment?
Yeah, so you basically you get 2 cents for answering a questionnaire with mTurk. So it's not very lucrative, but if you have the time to basically do that, then you can earn a couple of bucks with that. Yes.
Is crowdsourcing the same thing as the bias scale?
It's what?
Is crowdsourcing the same thing as the bias scale?
Bias?
As like we talking about what the lies can be. So is it the bias scale that you choose to answer the question?
No, it's a bias, not biased. And you mean from the biased sample from the visual displays?
Yeah, like if you choose to.
Yes, it is a bias. You're right. You're right on that. That's well observed, well connected. Thank you. Yes, it's a biased sample because essentially what you're looking at in a convenience sample, if it's not generalizable, that was not the slide I wanted to show. This one. If it's not generalizable, essentially you speak about a bias. So this difference from your sample mean to the population mean, this is called a bias. This is a so-called selection bias. So this is the problem with mTurks, and this is also the problem with testimonials, because if you try to look up reviews online, we all have looked at reviews, and we base our shopping at least partly on reviews. If there are a lot of positive reviews, we feel more reassured, and we feel a little bit more confident about making good choice. The problem with testimonials is, though, that who's writing that testimonial? It's either really a super satisfied customer, or it's a customer that is really, really angry at the manufacturer because he or she didn't like the product. So there is again a bias.
Yeah, extreme.
Exactly. And these extremes are not representing the overall population, because nail polishes, you have, maybe you have for this nail polish 1,000 reviews, but essentially millions of these nail polish bottles have been sold. Yes, so bias. Bias is not strictly avoided with random assignment, but random assignment reduces confounding. So bias and confounding are essentially 2 separate things. Self-selection into one group causes confounding, which is it's a little brother of bias, but it's not the same thing. But with random assignment,
Can you explain the difference with self-selection and confounding that's not fine?
well, in the randomized controlled trial, you would cause a bias. So this is where it is the little brother, but the differences between those two into a group would essentially be acting as a statistical confounder. So we will not go into the details between those differences. So you have, I think, I came across like 15 different biases. So there are different subtypes and there are different reasons how you look at that. So, but basically you have bias, confounding, and you have mediation. And these 3 are kind of very much interplaying to some extent. So what bias is really this deviation from the representativeness. So if the sample mean differs from the population mean. So random assignment is important because you have allocations into 2 different groups. So you recruit individuals, you tell them about your randomized controlled study, and you ask them to participate. And they're participating, then you assign them to either the intervention group or the control group. And this is done with random algorithms that you have to program. Random selection is almost never used, which is also difficult because that would mean that I'm picking you and you're going to come in the intervention group, right? So it's just practically not feasible. Any questions on random assignment? We talked about random assignment in the first class about if you remember, the wellness programs, self-selecting to be part of a wellness program, which will cause confounding between the 2 groups and therefore act in a bias. Then we have probabilities. Probability, we're not going to do much probability. We will do a bit of it. You get probability. I take you have learned probability in high school. So the probability of rolling a 6 on a die is 1/6, right? If you're rolling the die twice, it's 1/6 multiplied by 1/6. So this essentially, it's a mutually exclusive event, which means the probability doesn't change just because you rolled the die before. That's the gambler's fallacy. I don't know who of you have ever been to Vegas. So you see in the casinos, you see the last numbers, and some of the gamblers, they're sending out, now it was 4 times red in a row, now black has to come. Is absolutely not true. So this is an erroneous thinking, which I guess qualifies as what is labeled here as an illusionary correlation. We're having also so probability is being used because you can infer dynamics in a population based on what you see in your sample. So if you have a sample, for example, we're getting to that later. So it's basically you're using probabilities that you have drawn from your sample to extrapolate them to your population. So if you see in your sample, for example, you see a certain risk of having to go to the hospital, you assume that the probability of your sample will be representative of the probability of these individuals in the overall population. So you're extrapolating it to the overall population. Yes?
When do you know that you have a good enough sample to extrapolate it to the population?
Well, never. That's the problem. But you test your sample, so you will compare those means and medians to that information that you have from the population. And we will do that with hypothesis testing. So if it's really far off, then you kind of have a non-representative sample, and you have to treat it somewhat carefully, cautiously, and interpret and draw inferences with caution. Then with replication, you also see whether these dynamics are the same in 10 different studies on the same topic. If this is the case, then you get a little bit more comfortable about it. But there's no golden rule. Okay, so you have to do that.
Do you have to include outliers when you're doing probability?
No, outliers are actually part of the estimation. So excluding outliers actually can bias your results, your sample, to start with. So confirmatory bias is a confirmation bias. Is basically that you make your own assumptions about the probability of a certain event to come. So if you're already convinced that of a certain event happening with a certain probability, you will just focus on this being confirmed. So you will give it more weight than it actually deserves. Illusionary.
Can you give what more weight?
Let's say I always knew that I don't know, it's gonna be hot in summer, and then it's cold one day and hot the next day, and so you see yourself confirmed, and that therefore you weigh it more than it actually deserves, something along these lines. Illusionary correlations are correlations that are just in somebody's mind. This is like I'm running fast on a race when I wore the talisman that my grandmother gave me. So that's kind of like along these lines. Good, but what is really important is now, so personal probabilities are subjective probabilities, where made up numbers are essentially used to state faux or fake probabilities. When I, for example, say like there's a 10% chance and I'm gonna have, I don't know, dinner after 9 p.m. today. So when I make up my own probabilities. So this is also rather to be saying cautiously. Basically what you see is you have probability is determined by successes over trials. So if you have 100 trials and you pick randomly 100 people from your population and 40 of these are diabetics, you know that there's a probability of 0.4 or 40% that from the sample you're gonna randomly pick a diabetic if you pick only one. So that's essentially how you have to look at this. So the probability is basically you have a certain probability derived from the sample population, and then you can extrapolate it to the individual. Equally, if you have trials, outcome and success, so you want to pick diabetics, and you study a small sample. You study those 100 people. You have 40 in there, and that gives you a probability of 40%. If you replicate now and you do this trial of 100 people, you're doing that 20 times, and you get 20 times, you get a different probability estimate. This probability estimate will essentially normally distribute. So you get 40% first time, 38 the second time, 42 the third time, then 43, then again 39, 37. So you get a normal distribution, where the center, the mean of this distribution of all these different estimates essentially gives you an idea about the probability in the population. That is the idea. Yes?
How can you be getting the normal distribution if you're getting a different probability of the time?
Because you basically use all these different probabilities from each of your trials as a data series. So you basically use these 20 different probabilities of your 20 trials of each 100 people that you randomly sampled to get one data point. So you have 20 data points, and these 20 data points basically have an average. And this mean essentially is reflective of likely what is that probability or that proportion in the overall population.
The mean is what the likelihood.
The mean, yes, because you assume that this is a normal distribution.
We're not confused because if you're, let's say you're interviewing or you do with 100.
Let's do the exit. No, we're actually over already. No, 6:15. 6:15. 10 more minutes. Okay, so this is worthwhile exploring. So we have, let's say we have a sample of 100 people. Sample of 100 people. And we get for the first time, we get 40%. Then we get 32%. Then we get 34%. Then we get 43%. Then we get 45%. Then we get 37%. So now you have each of these trials had each 100 participants. So you get 100 people, and you get one probability estimate for each of your trial. And this is the probability from each of those samples. If you map this out, you get again a frequency distribution of your estimate. You treat it as a continuous variable. You get a mean, and you get a standard deviation around that. And this will be quite important for the hypothesis testing, because you do these random samples, you get each time you get one estimate. And this frequency distribution describes your sample distribution, how it likely will look like. It has a standard deviation, it has a mean, and the mean of all these trials is likely reflective of what can be seen in the population. That's the fact of replication. And this actually is being utilized when you try to quantify variability and do hypothesis testing with percentages, so with counts, because you utilize the law of large numbers. And the law of large numbers is nothing else that the more people you study, the more accurate your estimate becomes. That means that if you study samples 20 times of each 100 people, it basically with each sample you get a more accurate estimate of the true proportion or true percentage of the population, which equals the probability of randomly drawing a person that is diabetic. Does that make sense? I hope it does. It's a central concept. So, okay. So that's the law of large numbers. So the larger the number, the more accurately it depicts the proportional probability in the population. Independence and probability, it's important that they're independently sampled. So these samples need to be drawn independently, and they need to be independent of the outcome. So they really have to be independent. So we have probability is successes over trials. So this is 40 diabetics over 100 sampled people. And this also means if you do something 100 times, the number of successes of picking a diabetic is basically a success. So this is how you have to look at this. The confidence is a personal probability in the probability of an event occurring or not. So we will talk about the confidence interval. So the confidence interval and the margin of error is usually a 95% confidence interval. And this describes an interval within which you're 95% certain that you're capturing your population mean based on your estimate from the sample. So you basically, it reflects a probability with which you're confident or certain that you have a certain event occurring or not, which is in that case that you captured the population mean. And so all of these probability estimates are basically done to conduct inferential statistics. So inferential statistics are basically where you employ the rules of probability for the testing of hypotheses. So this is, for example, let's think of high. Not yet, not yet. It's not, t-test is not really, well, it is a problem, yes, yes. So the t-test is basically you are comparing to, so there are different t-tests. Yeah, so we're starting off with a SET score and SET test, where we're comparing a mean of a sample to the mean of a population. And the probability there comes into play because we're trying to make the case that a sample is different from the population mean, so that the sample mean is different from the population mean. So you have a null hypothesis under which you assume that there's no difference, that they're identical, and you have an alternative hypothesis under which you assume that the sample mean is different from the population mean. Probability comes into play because we are essentially testing what is the probability of the null hypothesis being true as opposed to the alternative hypothesis to be true. And we will only accept the alternative hypothesis if we have a confidence of 95%. And that's where the 95% comes in, and the so-called p-value of 5% as a type 1 error alpha criterion. But yeah, so this comes later. But essentially, a t-test is one way. Another way of looking at this is the probability of somebody going to the hospital. So this is actually, you can build probabilistic models that basically will give you a probability for an individual of certain age, certain blood pressure, certain gender, certain race, certain medical history to have to go to the hospital within the next 6 months. And this is actually part of the work that I'm doing. I'm predicting individual outcomes. I built on a population, I build a model, and then I'm trying to employ these models to individuals and try to flag those models and try to flag those individuals that are at the highest risk. So this is inferential statistics. So you draw insights and conclusions based on your population, and then you mean in a further step, employ it on smaller samples and patient groups. So we have a null hypothesis where there's no difference. Talked about this briefly. Then we have a research hypothesis where there's actually a difference. That means sample mean is identical to the population mean. That's the null hypothesis. Sample mean different from the population mean. That is a biased sample, and this is to be tested under the research hypothesis. Yes. Groups, we talked about it, control group, experimental group, or intervention group. The intervention group is the one that gets the blood pressure medication, whereas the control group does not get a treatment. we either reject the null hypothesis and accept the research hypothesis, and this will be done with a p-value or probability. So again, here's the layout. So we have a null hypothesis with no change. The decision is to either fail to reject the null hypothesis, will basically lead for you to accept this. If you reject it, you're basically accepting the research hypothesis. You can do this at a certain error rate, and this error rate is quantified as the so-called type 1 error, which is supposed to be smaller than 5%. Once your p-value is smaller than the threshold of type 1 error that you set, you will reject the null hypothesis. A type 2 error is when you fail to reject the null hypothesis, although you should have rejected it. And that's usually because you studied not enough people in a randomized controlled trial, for example, because you didn't have sufficient statistical power. Okay, last slide. Shocking prevalence of type 1 error. Positive outcomes are more likely to be reported than null results, and this is a problem because type 1 error should not occur, but people want to essentially have a significant difference because it basically publishes better. And that's unfortunately true, and this is the point they want to make. And there is a slide on one of the following where basically these studies that report a p-value that is slightly below the threshold of 5% are very frequent, which basically indicates that there was some outlier exclusion, some subsetting that brought the study just closer to get over the edge, just to be published as a significant result. Good, and that's it. All right, thanks so much. Enjoy your break. We see on 1024 again.
Hi.
Hi.
Okay, I have a few questions. First, when I put the proportions, it makes it